Welcome to the BRTRPS Sprint 3 demo video from Team 3. Here are the members of our development team. In this sprint, our work revolved around a single guiding objective, completing the assigned mission of tracking a high-value asset from point A, distribution center, to point B, destination point, with precision. For that reason, our set of user stories was structured to support and fulfill this mission end-to-end. We highlight the following user stories. US 3.3.1 Physical Link Integration. US 3.3.2 Unified Architecture Documentation. US 3.3.3 Delivery Route Visualization. US 3.3.4 API Adjustment for Real GPS Data. US 3.3.5 Graphical Unification of HMIs and SCADE. US 3.3.6 Algorithmic Modeling of the GPS/Freedoms Architecture. US 3.3.7 Algorithmic Modeling of the Launch Plan. We implemented the communication channel between the two Freedom boards, combining UART for board-to-PC transfer and UDP for PC-to-PC data exchange. A structured GNSS payload, a framing format with CRC, and small Python bridge scripts ensured that telemetry could move reliably from the simulated satellite to the ground station. In US version 3.3.2, we have combined all architectural diagrams and interface definitions from specifications Team Scrum 1 and Team Scrum 2 into a single reference document. We enhanced the web HMI to receive real GPS coordinates and plot the path dynamically on the map. The interface now supports destination selection, automatic route recalculation when the user deviates, and display of raw telemetry from the Freedom board. This fulfills the sprint's main objective, showing an end-to-end delivery route using real data. The ground segment API was updated to parse real GPS packets, validate latitude/longitude ranges, timestamps, and data consistency that a dedicated endpoint now receives the data, stores it briefly, and serves it to the web interface with low latency. This enables the continuous map visualization built in US 3.3.3. Space segment shows the simulated satellite data, orbital parameters, basic telemetry status, and the GNSS-like payload generated in SCADE. It lets the operator confirm that the satellite model is producing valid data to be sent to the ground. We then have the following for the space segment. Satellite 1 sends, the ground receives. Satellite 2 sends, the ground receives. Satellite 3 sends, the ground receives. The ground segment performs the calculation. It sends the computed position back to Satellite 1, then to Satellite 2, and finally to Satellite 3. Once all three satellites receive the updated position, they replicate it and transmit it to the user. Only then does the GPS fix appear. This cycle repeats continuously. Ground segment displays the decoded data received from the physical link/API, latitude, longitude, speed, UTC time, and message validity indicators. It confirms that the ground system is receiving and processing telemetry correctly. So, everyone, this application we are running with SCADE handles the graphical interface for the Freedom board, collecting GPS data. On the right side, we can see the collected data being replayed at a faster rate, 200 milliseconds. SCADE allows us to reproduce this data on the graphical interface, increasing or decreasing the playback speed. With that, we can check the timestamp, latitude, longitude, sensor accuracy at each moment of the collection, speed, and heading. We can observe that during the curve, the heading changed to 300, pointing north. We documented the core logic behind GPS data processing, including coordinate conversion, timing behavior, and error metrics such as GDOP. The model defines how raw satellite measurements are transformed into usable geographic information, preparing the system for future embedded implementation. For this user story, a study was developed presenting a pseudo-algorithm model to determine ideal launch windows for 4 navigation satellites. All developed user stories were made available on GitHub, along with the team's Kanban board. A continuous follow-up of the activities was carried out to generate a burn-down chart at the end of the sprint. Thank you for your attention.